Okay, so when we talk about soils, we can get into some pretty heavy-duty jargon pretty quickly, and that's not what this lecture is about. That's another whole class. But it's kind of useful to pay a little bit of attention to some of the classification system of soils, because they were organized based on some principles that relate them to the parent material, the geological substrate that they're formed from, the time, how old they are, and weathering intensity, by which I mean the climate and the biology. And so I just have a few examples here. This is an example of an aridisol, which is a desert soil that accumulates calcium carbonate. And you guys are lucky to have two experts on isotopes in carbonates that are going to, Naomi and Katie are going to be giving you some more detailed background on carbonate formation and the signals that we can get out of that. So that's just one example there. Here's examples of two different soils that accumulate organic carbon as opposed to the inorganic carbon in the desert soils. Histosols are like wetland soils, like in Everglades or like in a lot of peat areas in the boreal forest. Mollisols are formed in grasslands, and that really dark color there is partly from root carbon, but also partly from charcoal, because a lot of grasslands have fairly frequent fire return intervals. And so that a large part of that carbon sticks around because it's actually charcoal or biochar. So our concepts of soil organic matter are actually changing. The kind of classical approach to thinking about soil organic matter is to divide it into three conceptual pools with different turnover times. Okay, we've got these concepts are changing a little bit, but they're still useful. So we've got the active pool, the labile pool. These are made up of simple compounds like sugars. Okay, oh look, looks like we've got some substrate right here. Substrate. Pass it around. All right. So it's not just us that likes that substrate, it's the microbes too. I didn't bring it in, I promise. It was just there. Okay, so I just admitted, you know, we're all like microbes. We love that quick carbon, right? That quick substrate. That's the labile pool. All right, we've got the slow or resistant pool. Hopefully this morning you all had some granola or something that's going to stick with you for a little bit longer. This is made of cellulose, lignin, stuff that takes longer to break down. We think of the passive or stabilized pool as being microbial byproducts. Oftentimes these could be long-chain alkanes, but it's actually quite complicated and challenging to understand what passive soil organic matter is chemically. Okay, so there's still a lot of kind of mysteries into what makes up this, what makes stabilized carbon have such long residence times of decades to centuries. So, and so more and more research is going into this because, of course, it has climate change implications. And so nowadays we're thinking about stable soil carbon being protected as opposed to being passive. Okay, and so this is kind of a nice little conceptual figure. I cannot claim credit for it. And so different ways that soils, stable soil carbon can become protected from decomposition is by, here's some examples, physical disconnection, like for example inside of aggregates. The soil carbon can be protected from enzymes. In sorption mechanisms, you can have bonding to clays, but with the organic matter to clay, and that also protects it from decomposition. And of course, freezing and thawing. There's a lot of carbon stored in permafrost, right? And that's one of the things that a lot of people are recognizing. There's a massive amount of carbon. We don't really know how much carbon is stored in permafrost, and with and with climate change, it could become quite vulnerable. So now we think of soil carbon as being really quite dynamic and potentially vulnerable to losses from climate and also from land use change. So this pool that we used to think was passive or inert, now we recognize it as being physically stabilized, but potentially vulnerable if there's some fresh carbon that gets in there to help decompose it, freezing or thawing, or other processes that can destabilize it. And so when we're doing soil organic matter research, it turns out that there's all different sorts of methods that have been developed. I would say probably some of the earlier methods related to chemistry, the chemists got involved. And that was quite classic, a number of different acid types of dissolutions. And people don't really do those so much anymore because they realize actually they're creating compounds that didn't exist in the soil. So a lot of these harsh chemical extraction didn't actually do extractions. They were creating chemical reactions and creating stuff that doesn't really exist. So people don't do those so much anymore. Physical fractionations, however, are still quite useful. And these are based just on particle size and or potentially on density classes. We can also do biological fractionations. Basically, you put dirt in one approach we're doing with my lab group. We put dirt in a jar and let the microbes tell us what's available, right? And so that's a way to demonstrate the microbially useful or labile carbon. And of course, okay, 20 minutes in, we're finally going to start talking about stable isotopes. And so they can be useful on their own, just looking at bulk soil carbon. We can also use them with other types of methods. And I just want to have a quick pause. What do we mean by fractionation? I've used it in a number of different places on this slide. So what's fractionation? You guys know this? Separating things out into different categories, right, at its most basic level, right? So we have isotopic fractionation, but we also have, maybe chemical sort of fractionation, physical fractionation. You've got the big particles separating out from the little particles. And so so I'm just trying to throw a word of caution to remember when we're using jargon, remember that your jargon might mean something different to someone else, even though it's the same word, right? I've learned a lot about that in Australia. Okay, so good. And so I'll talk today also about natural abundance as well as a little bit about tracers. Have you guys talked about isotope tracers yet, like applying non-natural abundance? Yes, okay, good. Okay, so it won't be new. So here's an example of when we can use physical fractionations to assess carbon storage in aggregates. And yeah, soils are really amazing. We can start getting into kind of the microscopic details of the aggregates, which are just the little clods around a root. And we can see that, there's a root hair inside of this soil aggregate that's sort of forming around the root hair. There's protected soil organic matter, especially after the root dies. These aggregates are often forming with the help of mycorrhizae, which are symbiotic fungi with plants. And they have hyphae, and they exude this stuff called glomalin that's a kind of a protein type substance, and it sort of glues together the little PEDs, the little aggregates. Okay, and so plant litter, so there's soil aggregates, but then we also have plant litter that's, obviously you can see it, you can recognize it, but then it can just break down into smaller particles. You can still tell it's plant material, but so we can call it particulate organic matter, okay? And so then we also have all different sizes of aggregates, microaggregates, and I actually took out a lot of these details because I think that we can get a little bit obsessive compulsive about, how we do our soil physical fractionations. And so I kind of sparing you a lot of the details, but I kept a few examples because I think it's important to at least look at a little bit of data and not just concepts, right? You guys are used to data, right? So let's look at this example. This is a book chapter that I recommended in your reading list. I don't know if I actually assigned it as required reading, but if you're interested in this stuff, I can get you a copy. It's a pretty useful chapter. So here we can see that there's a bit of a range. This is in what kind of soil is this, a C3 or a C4 soil? C3, okay, because it's around minus 25, 27-ish, right? And so we can see that the finer particles, the clay boundary is less than 2 microns, right? So this stuff, even especially the fine clays, they're more enriched, higher delta C13 values. And these coarser particles, the sand-sized particles, have kind of more of a range, right? But they also tend to be lighter. So they're more like, actually like the plant inputs, right? Maybe because they have more lignin. These types of patterns have been observed in a lot of situations, but we still don't know exactly why. Okay, so there's still a lot that we don't completely understand about the processes that are going on to lead to these observations. Here's another example with binding organic and a kind of a representative chunk of soil organic matter to a clay mineral. And so we think this is a little bit of an old diagram because we used to think of soil organic matter as being made up of a lot of phenol groups that are all linked together. This is sort of a bit going out of fashion. We don't know if that's really true. There's certainly a lot of lignin in plant material, but then oftentimes it seems like that lignin is getting transformed into more stuff that's more like waxes and lipids, okay, and microbial lipids especially. But at any rate, the point here is that there's a bunch of functional groups that can bind to the clay minerals. And so what is so special about clay minerals, you people who are so interested in clay layers? What's so cool about clay? It's charged. It's charged. It's highly charged. Okay, that's one really important thing. It's negatively charged.
Relatively impermeable, sometimes if you get a good one.
Yeah, it can be relatively impermeable. So, and that could actually maybe keep things out. That's what I think of when I think of impermeability. So that might help protect the carbon that gets stuck into there. What else is special about clay? High surface area, exactly, right? So depending on the type of clay mineral, you could have a very high surface area. Okay, some clays have higher surface area than others, right? So there's a whole lot of different clay minerals that have formed in soils. They're pedogenic. We call them pedogenic because they formed in soils in situ. They're secondary minerals. But have you guys heard of biotite? Probably a lot of you guys have seen biotite. That's a primary mineral. That's a phyllosilicate. And so you can think of clay, pedogenic clay minerals like smectite as an example. It's kind of like biotite. It's a plate-like structure. Okay, and so it has very high surface area with negative surface charge that can bind a lot of different types of functional groups. So why does it become enriched in C13? Okay, well, we can hold that thought. We're going to kind of keep looking at a few different pieces of evidence here. So this is actually from a paper that Dave Bowling wrote when he was a postdoc, where he went to a series of sites across a humidity gradient in the Pacific Northwest. And he's looking at a depth transect. So he's got the litter layer, the fresh litter, the old litter, and the mineral soil organic matter. It's a C3 site. But we see this really strong change in it's increase in the delta C13 value with increasing depth, right? But the enrichment is stronger in the wet site than in the drier site. You guys believe me? I mean, it looks like it's maybe double in the wetter site than in the drier site, at least. What's going on? What are some general differences between wet and dry sites? Microbial activity, right. I mean, it's probably have something to do with microbial activity. So I don't know if they controlled for age or parent material, so there could be other things like that going on because ecologists can't always find the perfect site that's the perfect, perfectly different only in one factor. But yeah, so there's probably something going on with microbial activity that's causing an increase in the enrichment of C13 with depth in the soil. Okay, and so here's another example, also from that book chapter, of that kind of demonstrates how the delta C13 value, look, the axes have changed, how the delta C13 value can increase with depth, we just learned that, but also with the age. Okay, and so how many of you guys know something about what this symbol means, that capital delta C14? So chat with your neighbors and see if you can figure out what this is saying.